How's it going, folks? Welcome to Diff Calc. This is week 3, video 1. Today we're going to be looking at concavity and points of inflection. Let's go and get started. So when dealing with functions, we can think of them as either concave up, where the function looks like a smile, so something like this, or concave down, where the function looks like a frown. Now, it doesn't just have to be a full frown or a full smile. When we're thinking about concave up, we can have a half of one, or a half of one going this way. When we're thinking of concave down, it doesn't have to be the whole one. It can be half of one as well, looking like these two here. When the function switches from concave up to concave down, so essentially when the second derivative is equal to 0, this is known as a point of inflection, okay? It's going to be abbreviated as POI. This is going to be very important. So whenever the second derivative is equal to 0, you're going to get a switch from concave up to concave down, or you can have it from concave down to concave up. Okay, we're essentially just combining these halves of our concave pieces. So we will use the second derivative, which is acceleration, to determine if a function is concave up or concave down. So our definition of a concavity is as follows. We're going to let the function f be differentiable on the open interval I. The graph will be concave up on the interval I if f prime of x is increasing, which essentially just means that the second derivative is positive on the interval, and concave down if our first derivative, f prime of x, is decreasing, otherwise known as when f double prime of x is negative on the interval. So if we're concave up, we know the derivative it will be increasing, so our velocity is increasing, and our acceleration will be positive. We're going to be concave down if our derivative or our velocity is decreasing. In that case, our acceleration or the second derivative will be negative. So below are sketches of the graph or of the function 1/3 x cubed minus x and its derivative on the bounds. So this is just a nice little example as to see what happens when certain things occur. So in our first function, we can see a couple things. We're going to have a relative maximum here. So at -1, we have a relative max in the original function. On the derivative, we have a 0. So we have a critical number. At x equals 0, we're going to have a point of inflection. Okay, we go from concave down to concave up. Notice how at our point of inflection, our derivative will have a relative minimum here. Essentially, our derivative here is going to have a slope of 0 at this location. And then our final thing, we have a relative minimum here. And we can see at that relative minimum, we again have a critical number. Okay, big picture item here, though, for today is that when there's a point of inflection, the derivative's derivative, so the second derivative, will be 0. So testing for concavity. Let f be a function whose second derivative exists. The first thing you're going to do is find the points of inflection. You're going to test points in between your points of inflection in f double prime of x. If your second derivative is greater than 0, the function will be concave up. If the second derivative is less than 0, the function will be concave down. So let's do one example here. We're going to determine the points of inflection and discuss the concavity of the function. So the first thing we need to do here is find the first derivative, which in this case will be 4x cubed minus 12x squared. And then we're going to find the second derivative, which in this case will be 12x squared minus 24x. Now to find your points of inflection, or your POIs, are again when f double prime of x is equal to 0. So we're going to set our second derivative equal to 0, and then we're going to solve for our values of x. I'm going to go ahead and factor out 12x, so I have x minus 2. So I can see that my 2 points of inflection are going to occur at x equals 0 and x equals positive 2. So from here, I'm going to create a sign chart of my second derivative. So I'm going to have 0 and 2, and I'm going to substitute values into my second derivative. So I'm going to go ahead and check out let's check out f double prime of -1. If I substitute these values in, I'm going to go ahead and get 12 plus 24. That's going to be 36, which will be positive. So we're going to have positive there, not sideways thing there. We're going to have a positive value. Let's go ahead and check f double prime of 1. If I plug in 1, I'll have 12 minus 24, which will be -12 and be negative. And then I'm going to check f double prime of 3. So we're going to have 9 times 12, 108 minus 24 times 3, which is 72. So we're going to have 108 minus 72, which will give us 36 again, which is positive. So again, these are all plugged into the second derivative, okay? Please do not confuse this with the first derivative test. When we are testing for concavity, you need to plug it into the second derivative. Okay, so then our final thing is our conclusion. We're going to say that f of x is concave up on the intervals -infinity to 0 and 2 to infinity, because f double prime of x is positive, and we can say that f of x is concave down on the intervals 0 to 2, because f double prime of x is negative. And that's all I have for today, folks. Thank you very much.